Welcome back for our third lesson in Unit 2, which is all about flows of energy and matter. And we cover a lot of important information here because flows of energy and matter are basically what decide the amount of carbon-based life our planet is able to support. So let's get started. The first thing it's important to recognize is that all of the energy that we have on this planet comes from the sun. Our sun is a star. It's about 4.5 billion years old, and we think it's about halfway through its life. And you can see the sun, oopsies, you can see the sun up here in this diagram. So the energy that comes to us from the sun comes in the form of solar radiation. But not all of that energy is absorbed by the planet. In fact, about 30% of it is reflected or refracted in the atmosphere and the biosphere by clouds and off the ground as those sunbeams have their journey to the planet. The other 70% of it is absorbed, but some of that is absorbed in a way that's not helpful. If sunlight is absorbed by dust or clouds in our atmosphere, then we can't use that sunlight for anything very productive. Of the ground absorption, only about 0.06% of the solar radiation falling to the earth is captured and actually used. Because even in the process of ground absorption, the sun can go straight through a leaf, it can hit the wrong part of the leaf and get reflected off. So of the amount of sunlight that we start with up here, less than 1% of it supports all life on the planet down here. Because sunlight and solar energy is the basis of all life on our planet. And we're going to look a little bit at how that is structured in the next slide. So when we talk about sun energy, we are talking about plants being able to take up energy. And the name that we give that is primary productivity. Since plants are autotrophs, primary producers, we call the process through which they assimilate energy primary productivity. Gross primary productivity is the total energy uptake of a plant from the sun. But it doesn't use all of that energy just to promote the next level of a food chain. It needs to use some of it to stay alive. So gross primary productivity goes to power respiration, and it also goes to power growth of a plant. After those processes have been accounted for, we can look at what we call net primary productivity, the amount of productivity that a plant has to pass along to the next level of a food chain. And that can be measured by the growth of a plant, the rate at which a plant accumulates its dry mass. You can also say that it's measured as the gross primary productivity minus the amount of energy that that plant needed to put towards respiration. Once we get into talking about consumers, we are talking about secondary productivity. And gross secondary productivity is the total energy taken up by a consumer. And it's just measured as food eaten minus fecal loss because there's no energy in fecal matter. Net secondary productivity is all assimilated food that is used for growth in a plant, and you can measure that as gross secondary productivity minus respiration. And those math equations get important because the IB does expect you to be able to do some calculations, and your homework assignment for this lesson is going to focus on some of these calculations, so keep those in mind. When we look at productivity, we're mostly looking at energy passing from level to level. But that energy couldn't be passed along without the cycling of matter. So this process of productivity is intimately tied into cycling of matter. And in the next slide, we look a little bit at the difference between flows of energy and flows of matter in our world. The big difference is that energy flows in an infinite amount. There's a finite amount of matter on the planet, and it cycles. It cycles around from the biosphere to the lithosphere to the atmosphere and changes form, but we don't get any more of it. Outputs from these systems, from energy, the output you look at is heat. From matter, you look at nutrients that are released, but again, those nutrients are reused and recycled. The sun is mostly involved in our flow of energy, and atoms and elements such as carbon and nitrogen are primarily involved in when we look at cycles of matter. And there's actually 40 different major nutrients or elements that we can look at in cycles. When we look at a biogeochemical cycle, we can use what's called a nutrient model that shows the amount of that nutrient that's typically stored in biomass. Remember, the bigger the storage in a model, the more of whatever the substance you're looking at resides there. The amount that is in soil and the amount that is in litter. You can also have arrows that represent the processes that move these different nutrients from one storage to another. The two nutrients that we are going to look at most carefully are carbon and nitrogen. So the carbon cycle should probably look relatively familiar to most of you. You should be able to talk about some of the major storages of carbon. The biggest storage of carbon that we have is carbon that sits in the deep oceans. One of the concerns with global warming is as the oceans heat up, that carbon shoots into shallow oceans and then gets sucked up into the air. And that is carbon that then goes into the atmosphere and increases the carbon in the atmosphere, which is already facing pretty significant increases through the human activity of combustion. So that's one big human impact that we are having on the carbon cycle. We are heating up the oceans and taking that deep stored carbon and sending it up into the atmosphere. We're also sending carbon into the atmosphere through combustion because of the burning of fossil fuels. When we look at the nitrogen cycle, humans actually have a significant impact on the nitrogen cycle, but it's something that I think not as many people are aware of. So looking at the nitrogen cycle, I'm actually going to show just a picture of a nitrogen atom. So when you look at the nitrogen atom, you'll notice that in the outermost electron shell, there are only 5 electrons in a nitrogen atom. And as humans add more and more nitrogen through nitrogen-based fertilizers to environmental systems, we see these nitrogen atoms interacting with the soil and pulling other elements down and bonding with them because they want to fill up their outer shell of electrons. And in doing so, they undergo leaching of other elements and pull other nutrients out of the soil. So that's one big human impact on the nitrogen cycle. We are creating artificial nitrogen, and that nitrogen is leaching other nutrients out of the soil, which is bad news when you want to grow food, which is something that we'll talk a little bit more about in another unit that is coming up about land-based food production. But for now, let's go over some of the main processes in the nitrogen cycle. You should be a little bit familiar with these processes. Sometimes this information comes up on the IB paper too. Nitrogen fixation is when atmospheric nitrogen is made available to plants. We have a huge impact here through what is called the Haber process. We are artificially taking nitrogen out of the atmosphere and using it to create fertilizer so that we can grow food. Nitrification is when ammonium, nitrogen that's locked up in ammonium compounds, turns into nitrate so that it's readily available to living organisms. Denitrification is the opposite, and assimilation and decomposition is basically just as organisms get bigger, they take nitrogen in through their proteins. As organisms die, they give that nitrogen off in the process of denitrification. So those are just some good vocabulary words to be familiar with. And let's talk a little bit about when we look at energy and matter together, how we can calculate energy flow. So matter is important to energy flow because matter helps energy change forms. But when we look at energy flowing through a system, we need to look not only at how much energy there is, but how efficiently it's being processed. So we look at efficiency of assimilation of energy, which is gross productivity times 100 divided by the food eaten. And we look at efficiency of productivity, which is net productivity times 100 over the gross productivity. So how efficient is each level of production? Generally, we say that trophic efficiency has about 10% of usable energy passed on at each level, but in reality, that number is a lot lower in plant-based passages and a lot higher in animal-based passages. So you see lower efficiencies lower in the food chain and higher efficiencies higher in the food chain. In modern agriculture, we look a lot at what is called an energy budget, where we calculate the energy entering a system, the energy remaining in a system, and the energy leaving a system. We look at that because we provide what is called energy subsidies through the use of technology or genetically modified organisms to increase our energy to yield ratio so that we can make more food. And there are some good numerical calculations that you can do around productivity, and that is what you're going to do in your homework. So let's take a look at your homework slide. And if you're following along with the book, your optional reading assignment is up here. The math-based question that I would like you to work on, because it is important that you're able to do simple calculations and have a good understanding of graphical information, is this 4-part question based on this table about net productivity and respiration values in different trophic levels in a food web. So try to work that out. When you're ready, you can go on to the review video and we will go over exactly how you do all of this. I will see you there.